Good afternoon. In the last class we
Good afternoon, sir.
Good afternoon. Last class we discussed work required for a compressor without clearance volume, and today we will discuss the work required for a compressor with clearance volume. And the formula for work required compressor work is this one in terms of temperature, gamma by gamma minus 1 multiplied by mRT1 T2 by T1, and in terms of pressure the relation is this one, and in place of mRT1 we can also write P1 V1. That is for adiabatic process, and generally the processes are not adiabatic, so we can use the formula for polytropic process where n is the polytropic index, and the formula is same. In place of gamma we put n, and value of n may vary from 1 to gamma. 1 means isothermal, gamma means isentropic process. So from PV diagram we can see the work done during the process is actually this area without clearance. This is the PV diagram, and work done is this area 1, 2, 3, 4, 1. This is the area, and this area represents the work done or work required for single stage compressor without clearance volume. Now let us see how we can deduce the formula for work done for the same single stage compressor but with clearance volume. You do not consider this line. Suppose this is the process. So work done, if there is no clearance volume, then it will be 1, 2, 3, 5, 6. 3, you forget about 3. 1, 2, 5, 6, 1. So this is the work done for without clearance volume. So the process is 1, 2 is compression, 2, 5 is delivery, 5, 6, 1 is suction. And so this time we will consider that suppose these processes are not there. So what will be the process in this case? The process will be 3, 4, 6, 5, or we can say 3, 5, 6, 4. And in that case, the work done is this area, this orange, yellow color area. This is the work done. It may be work done on the system or work done by the system, but this is as a whole, this is the work done if it is a clearance volume. Now let us see how we can deduce the formula. So you look at the PV diagram. Process 1, 2 is compression, and 2 to 5 is delivery, but the delivery process is completed at point 3. That means before reaching the final cylinder. So 3 is correspond to this, V3 is correspond to the clearance volume. So this Vc is the clearance volume, Vc equal to V3. So that means the piston moves from BDC to TDC, but before reaching the TDC, it will again, the process will be 3, 4. Now from the diagram you can see process 1, 2 and 3, 4 are opposite process. So 1, 3 is compression, and 3, 4 we can see opposite means this is expansion type process. So whole process cycle is 1, 2, 3, 4 and 1. So this is the work done during whole cycle. Area under the curves is 1, 2, 3, 4, 1. This is the work done. and from that we will get work required with clearance volume. So we have to find out work required with clearance volume, and this PV diagram is a compressor with clearance volume Vc or V3, and the work will be equal to 1, 2, 3, 4. We have to take some assumptions. Let both the expansion and compression processes follows the adiabatic law PV to the power gamma equal to constant. This is the law. Isentropic we consider. C, clearance volume in this case is V3, shown in the diagram V3. Now what is the swept volume? Vs, that is equal to V1 minus V3. So this is V1 minus V3, that means this is the volume Vs, swept volume. Now actual volume is V1 minus V4, because this is the actual volume V1 minus V4 to V1, because actual suction takes place from 4 to 1 suction process. That is called the actual volume. Although the piston moves from TDC to BDC, that means from V3 to V1, but during the process 4-1, that means from V4 to V1, that is the actual volume involved during the suction stroke. Okay. So what will be the work done? Work done I have seen, I have mentioned 1, 2, 3, 4, 1. So that area, that is will be area 1, 2, 3, 5, 6, 1. 1, 2, 3, 5, 6, 1. This whole area minus area 4, 3, 5, 6, 4. This area we will deduct. And what will be the remaining area? 1, 2, 3, 4. In the previous chapters, we have deduced the formula for single stage. So what will be the work done during the area 1, 2, 3, 4, 5? So what will be the area? Gamma divided by gamma minus 1 into P1 V1, because the process is 1, 2, multiplied by P2 divided by P1 whole to the power gamma minus 1 by gamma minus 1. That means this is like single stage compressor without clearance volume, minus this area. So minus, it will be same 3, 5, 6, 4. This is also like a single stage compressor in case this is expansion process, single stage process without any clearance volume. So that will be equal to gamma by gamma minus 1 into the pressure is P4 V4 multiplied by, okay. So now you look at this PV diagram, you can see P3 equal to P2, also P1 equal to P4. So we can write P3 divided by P4. What is this? P3 divided by P4 will be how much? P3 divided by P4 is equal to actually P2 divided by P1. So if that is so, this term we can say this will be P2 divided by P1. So we can write that is equal to, this is common and this part is also common. So you take the common gamma by gamma minus 1. Now what is common? P2 divided the first part and the second part. Now what left? P1 V1 and P4 V4. Now we can see P1 equal to P4. So this is equal to P1. So we can also take common P1. So only V1 minus gamma by gamma minus 1 into P1 into, now you see what is V1 minus V4? We call it actual volume VA. So that is equal to VA. Finally, we get work required for the compressor with clearance volume is, and also we can write in terms of temperature, it will be gamma by gamma minus 1 P1 VA. This we can write T2 by T1 minus, again you see gamma by gamma minus 1. So P1, this is like P1 V1, so we can write MR T1. It is working in the temperature T1 itself. So that is equal to T2 by T1 minus T1. So any formula you can use. As per our requirement, we will use this first one or this one or this one. You need not deduce any formula for two-stage compressor. You only have to know the principle of two-stage compression. The principle is, for two-stage compression, we need one intercooler in between. And you should also know the advantage of intercooling. Advantage of intercooling is that it saves some work, because compressor consumes work, and if we do intercooling, then the total compressor work decreases because of the intercooling. You can also see this diagram compared with this compressor, reciprocating compressor. So this is the TDC and this is PDC. What is this valve? Red one said this is the delivery valve or exhaust valve, and the blue one is suction valve or intake valve. That means air enters through this valve and it is delivered to the receiver through exhaust or delivery valve. And this is the volume occupied after compression, and this is called the what volume? The clearance volume, VC. This is VC, this volume is VC, clearance volume. Want to tell you, that is the law, T2 divided by T1 equal to P2 divided by P1 all to the power gamma minus 1 by gamma. This is called isentropic law, that is deduced from the PV adiabatic law and gas law. This is isentropic law. That is why in the beginning we assume that the processes are isentropic, and that is why we are using isentropic law. Now we will see what is volumetric efficiency, eta V. The volumetric efficiency for statement is, this is the ratio of free air delivery to swept volume. Now free air delivery is VA, actual volume, VA, that is V1 minus V4 divided by swept volume is VS. So V1 minus V4 is free air delivery, and you see V3 equal to VC. This volume, you see, this is swept volume. You look at the diagram, reciprocating compressor below. This is yellow one part is the swept volume. Next you see, this volume is free air delivery, V1 minus V4. This is V4 and this is V3. So we can write eta V is equal to, in place of V1 we can write from the PV diagram, you can see this is equal to VC plus VS. So we can write VS plus VC minus V4 divided by Vs, and that is equal to 1 plus Vc divided by Vs minus V4, and this is equal to 1 plus C minus with V4 divided by Vs. V4 divided by Vs, and this C is equal to Vc divided by Vs is called clearance ratio. This ratio is called clearance ratio. So we can write 1 plus C minus V4 divided by Vs. If we multiply by Vc and also divide by Vc, then the whole relation will remain same, and that is equal to 1 plus C minus Vc divided by Vs into V4 divided by Vc. That is equal to 1 plus C. This is again is equal to C multiplied by V4 divided by Vc. You see Vc equal to V3 divided by V3. Okay. Now for the process 3-4, which is an isentropic process, we can write V4 divided by V3 is equal to P3 divided by P4 all to the power 1 by gamma. Say for a process 3-4, P3 V3 to the power gamma is equal to P4 V4 to the power gamma, which is the isentropic law. Therefore, P3 divided by P4 is equal to V4 divided by V3 all to the power gamma. Say this is equation 1. Similarly, we can write from the gas law P3 V3 divided by T3 is equal to P4 V4 divided by T4, and from this also we can write P3 divided by P4 is equal to P4 divided by V3 into T3 divided by T4. From this directly we can write V4 divided by V3 is equal to P3 divided by P4 all to the power 1 by gamma. And again, if this is equation 2, from these two equations we can write V4 divided by V3 all to the power gamma is equal to V4 by V3 into T3 by T4. From this we will get V4 divided by V3 all to the power gamma minus 1 is equal to T3 divided by T4. So actually we need only this equation in terms of pressure, and if we have to find what is V4 divided by V3, then it will be equal to T3 divided by T4 all to the power 1 by gamma minus 1. Okay. So we will take this equation, and that is why we write V4 divided by V3 equal to P3 divided by P4 all to the power gamma 1 by gamma. And we can take common for C, and that is equal to 1 minus, in place of P4 by V3 we will write P3 divided by P4 all to the power 1 by gamma. And also we can write that is equal to 1, if we take minus C common, then it will be P3 divided by P4 all to the power 1 by gamma minus 1. Or we can write 1 minus C we see P3 is equal to P2 and P1 is equal to P4. So we can write, in place of P3 by P4, we can write P2 divided by P1 all to the power 1 by gamma minus 1. So this is the final equation for volumetric efficiency of single stage reciprocating compressor with clearance volume, where C is the clearance ratio, Vc divided by Vs, that means clearance volume divided by swept volume. So ultimately we get volumetric efficiency is equal to 1 minus C P2 divided by P1 all to the power 1 by gamma minus 1 in terms of pressure. We can also write in terms of temperature. Say from this equation, in place of V4 by V3, you can write T3 by T4 all to the power 1 by gamma minus 1. So we also can write 1 minus C T3 to the power T4 all to the power 1 by gamma minus 1 minus 1. Refrigeration. Air conditioning. Okay, thank you.